So the third talk of this session is a talk by Guillermo. Guillermo, if you want, you can already share your screen. Guillermo is giving a talk with Jürgen Jost on the evolution of chemical knowledge and how to study it. So Guillermo, the virtual floor is yours.
Thank you, Peter. And let me, you hear me? Yeah. Okay, I'm going to share, then let me know if, yeah.
Could be a little louder, Guillermo. It's very faint, or maybe closer to the microphone.
Yeah. Wait a moment. You see the screen better?
Yes.
And you hear me well?
Yeah.
Okay. Then I'm going to talk about, yeah, as is written here in the title, the evolution of chemistry. And let me try to measure my time. Yeah. This more than a talk with results. It had some results. It's more than the depiction of a research program. Because I would like to motivate people to try to work with me in this kind of new idea. But it's not that new after all. Then, how to start this then is how to study the evolution of chemical knowledge. That's more or less the idea of the talk. Then let's start by talking about these two fellows, Leopold Gmelin and Friedrich Konrad Weilstein. I'm pretty sure many of you know them, or at least the surnames and the books of them, because they were collecting a lot of information. For example, Gmelin, inorganic information in the 19th century. Actually, he started in 1807. And by the end of the 19th century, Weilstein started to do the same, but with a large group of organic molecules. They were collecting then chemical information, and when I say chemical information, I mean substances, reactions, properties, reaction conditions, and all where it's possible to annotate in a chemical reaction, and how chemists report the results on chemical reactions and on studies of the properties of substances. But then, with the pass of the time, the growing number of substances was very huge, and then fortunately in the 90s, all that information, that huge amount of information on substances and reactions was merged into one electronic database, which is called Reaxys. This database is nowadays owned by Elsevier. The approach we have here, what I'm presenting here, the research program I'm presenting here, is that we can explore, we can take all that information recorded in all those issues of journals and in Gmelin and Weilstein handbooks, can be.
Could you speak up, please?
Yeah.
Could you speak up a little bit louder, please?
Okay. Better? Let me see. You hear me better?
Yes, better.
Okay. Then what I'm saying is that all that information recorded in all those books and handbooks can be is nowadays electronically recorded, is electronically annotated, and then now what I'm saying here is that we can use mathematical and computational methods to try to address that information, because it's historical information at the end of the day, what we have there. Then the setting we have to study the evolution of chemical knowledge is this one, and is that chemical knowledge is based on the interaction, and this has to do with the previous talk, and is that is a complex dynamical system where we have the interaction of the material system of chemistry, the semiotic system of chemistry, and the social system of chemistry. The interaction of those three systems, from the interaction of that is that chemical knowledge emerged. Then we have here, for example, some instances of the material systems where we have materials, where we have substances, the instruments used to explore those substances and their properties. We have also chemical reactions, measurements. That's part of the material system. And now we have the social system. And in the social system, we have, for example, We have people, we have institutions, we have robots, we have political and economic and academic ties. I mean, those institutions and people and robots, they have some interactions, and those come from those relationships such as political and economic connections. The semiotic system is based on the ways chemists have used to explain themselves or to communicate one with each other. And we have molecular structures, properties, the way they communicate the properties, tables. We are very famous in science of using tables, not only periodic tables, but several other tables. Structural properties are also ways of communicating chemical information. And here we have also the important subject of chemistry of every science of meaning building of the subject we are considering. And this is the setting. This is we could put this in a mathematical framework, but the idea is that we have three systems which are interacting, and from that interaction we have the emergence of chemical knowledge. What I'm presenting here is not only is a program to study the evolution of chemical knowledge, but it's not only. One could take this as an approach to history of chemistry, and that's right. We could explore. We can, with all the data we have from the history of chemistry, we can explore the past and we can see how the knowledge is evolving. But also, if we are able to find patterns, if we are able to find some regularities in the evolution of chemical knowledge, with some statistical tools, we could even be able to do some estimations about the future of chemistry. But I'm not saying that we are going to say which is going to be the next important catalyst. I'm not saying, I'm not talking about those estimations. I'm talking about large scale patterns that could be extrapolated into the future. That's more or less the idea of those estimations or extrapolations. And that has to do with innovation. What I'm saying here is that this is not only important for the history of chemistry, but also for chemistry. Because if we detect patterns, then we could see, or we could try to address the point of knowing the driving forces leading to particular innovations or something like that. And okay, yeah, we could also be ready for particular perturbations of chemical knowledge. For example, the effect of pandemics. How pandemics are affecting the evolution of chemistry, because there have been several pandemics in the past. Then we can see the patterns and try to see how the evolution of chemical knowledge evolves according to those patterns. Let me give here some particular details of the social system and the fact that that social system is evolving. For example, here we have some instances of luminaries in chemistry. I'm pretty sure you know all of these guys. But the social system, as I mentioned before, is not only made of people. We also have, for example, here at the bottom, I'm trying to show with these three pictures the evolution of the laboratory. There is a connection, that's a negotiation between people and the places where they work. And chemistry is very famous about that, about developing the laboratory as a place to interact with matter. Then in mathematical terms, we could analyze this using, for example, network theory, where we have, I'm trying to depict this as a cartoon, where we have that every node here is a person or an institution or even a laboratory or something like that. But we also have, for example, here with this crown, I'm trying to put or to stress the role of the funding system, for instance, which is also shown here, and also the role of industry and academia. All those actors are interacting, and those interactions are evolving over time. We need to explore that. Now about the evolution of the semiotic system. The semiotic system is also evolving. And we can see here I have some very simple examples. And for instance, this is an affinity table. And an affinity table can be put in a mathematical framework where we have that every column here is an order set. Then that's the framework for analyzing affinity tables is order sets. But we could also talk about algebra. For example, Lavoisier, what he had at the end of the day was an algebra for chemistry, where you have different sets, and when you combine elements of those sets, you end up with some other sets, and then you start to build up all the hierarchy of chemistry. That evolution of the semiotic system has reached to, or has led us to, for example, another kind of algebra, which is more or less the one we use today with the empirical formulas, which was established by or introduced by Berzelius in 1814. If we go now, if we expand the dimension of chemistry, because now until Berzelius, we were considering just the composition of substances. But now, for example, a big part of this meeting have been devoted to molecular structure. Then we could take the molecular structure or we could set that idea of molecular structure into the idea or into the mathematical framework of topology, where we have the atoms, and those atoms, they are connected by bonds, so that they are sharing electrons. But what is important is that we have one set of elements, I mean atoms, and those atoms are connected by bonds. Those are the binary relations between those elements, and that leads at the end, that leads to a topology. But we can also sometimes, for example, people working in crystallography, they are not interested in the topology of the molecules. They are more interested in the geometry of the molecules. And you need to endow that topological structure with a distance, with a metric. Then you end up with working with metric spaces. Then the right setting for this is geometry. But this is very nice because I was trying to show that the evolution of the semiotic system, at least to talk about substances, was from text, I mean from the composition of substances, going to the topology of the molecules, the molecular structure, and then to the geometry of the molecules. But then the current way of encoding information is going back to text, which is, for example, the inches for molecules or the smiles, which are strings to be stored on computers, and there are several algorithms to work on that. That's more or less a kind of idea of the evolution of the semiotic system. And the material system is also evolving. I mentioned that the chemical knowledge can be taken as the interaction of the semiotic, social, and material system of chemistry. The material system of chemistry is made of substances and their reactions. Then with this kind of cartoon, I'm trying to show that, and I have here different historical depiction of substances. For example, that was used by the time of the Vainas, for example. Then we have here a lot of substances, which with the pass of the time, the number of substances is growing very fast. We have also different depiction of the substances that has to do with the semiotic system, but also the evolution of that space, that's what is called the chemical space. The evolution of that space is also attached to the instruments, allowing us to explore the interactions of those substances, for example. And I have here several examples of that. Yeah.
Guillermo, you have about 5 minutes left.
Yeah, okay. Then, okay, what I was mentioning was, okay, then we have the chemical knowledge, the material, the social, and the semiotic system. And then now we have, but then that's something like a dream, or that's, let's say, very abstract. But now we're going to talk about the reality or some results that we have obtained. Then there are data. Then we have, for example, electronic databases of chemical information, journals, patents, archives from the industry and different societies. We have different methods. And this publication, which is becoming a book, we have, but this is a preprint, you can already read it. This is a kind of summary of the book. We have mentioned these and several other methods that can be used nowadays to analyze the chemical information, and that bring some information about the evolution of chemical knowledge. Then I don't want to read this, but those are some mathematical methods that could be used to analyze chemical information. Then I'm going to discuss some results about that, and it's something like this is the idea of the evolution of chemical knowledge, and this is what we have done. just this small part of the tip of the iceberg is the evolution of the material system. And I'm going to go directly to the point, and is that we take the chemical space as the collection of substances which have been reported in the literature, which have been connected by chemical reactions. We studied this period between 1800 and 2015. This was the number of substances we used, and this were the number of reactions we considered. We counted year after year how many new substances have been reported in the literature, and then we found this trend, and that trend, this is in log scale, and here also, this is in log scale, and this is in linear scale, that's the time. We could find a trend. This is very interesting, a historical trend. It's something like the way of doing chemistry is leading, it has some regularity over the history. And that regularity has to do with the annual growth rate. Yeah, to summarize this is that about every 16 years, chemists have been able to double the number of substances. That is a very, very rapid growth of the chemical space. And the question is, which are the driving forces leading to this growth, and whether it's possible to speed up this growth or not. For example, chemical industry would be very interested in breaking up this historical record and doing rapidly. We found by analyzing the variability of this signal, using time series analysis methods, we found 3 statistical regimes, which we call the proto-organic regime, the organic regime, and the organometallic regime. Here, most of the compounds were more or less based on metal compounds, but also there were some with carbon hydrogen. This was a period where many of the compounds reported had carbon and hydrogen, and the percentage of metal compounds dropped. And here in this period, there was an appearance, and Jose Chamizo was mentioning something like this about in about 1980 something happened. Here was in 1860, and here is in 1980 something happened, and it was something like a revival of metal compounds, but attached to carbon. That means organometallic compounds. With that, we could calculate, or we could assess the effect of the world wars on chemistry. And I think this is important because we were not only analyzing the evolution of the chemical space, but we were also seeing how one social setback was affecting chemical production. Then I'm talking here about the interaction of the social and the material system. And then we found that the First World War sent back chemistry 37 years, and the second one about half of that time. That means that the First World War was very dramatic for chemical production, and there are historical reasons explaining this. I have some more time then. We also explored the how chemists, because then chemists are interested in getting to new corners of the chemical space. They try to synthesize new substances, and we found that they do it normally through synthesis. Then but how are there, let's say, patterns in those syntheses? And yes, there are some patterns. Those are the frequencies of use of some substances, and each plot here corresponds to one particular period. Here you have the periods. Then the take-home message here is that every year, could say that every year, many substrates have been used only once. Then you take some substance as a starting material, but you use it normally only once. That's the trend in chemistry. But there are some very few substances which have been used thousands of times. And normally those substances have been the same. It's something like a recurrent pattern. That was what I mentioned in the previous talk and with my question, that this is something like an instance of path dependencies. It's something that has to do with the way of doing chemistry. And some of these substances which have been very used over the history of chemistry are, for example, acetic anhydride and methyl iodide. And from the side of the products, we also have the same pattern. We see that many products have been synthesized only once. And I mean, if you work on a laboratory, then for example, you are doing your PhD on organic synthesis, then you synthesize your product, you publish the result, but you never go back to the same product. It's something like trying to populate in the chemical space. But anyhow, there are some recurrent syntheses of some particular products. Of course, here we have side products such as water, CO2, or hydrochloric acid, but there are also some particular targets. Then in general, what we see is that there is a kind of randomness in the way of exploring the chemical space, but somehow there is some particular starting materials which are preferred to explore the chemical space and also lead to some particular products with some more frequency than others. Do I have more time? No? Oh, okay, yeah. Peter is not looking at the clock then. Okay.
We have 8 more minutes, but that's including the Q&A, so it's up to you.
Okay, I'm going just to finish with this, and is that the idea is that the chemical space is expanding, and that's something that is part of my discussions on the periodic system, and is that many people take the periodic system for granted, and I think the periodic system is evolving. It's not for granted. Then, for example, when you try to understand the structure of the periodic system, my question would be when? When in 1869 or today? Then now with this kind of data we can explore the evolution of the periodic system year after year with the number of substances we know year after year. We can see how or what kind of shape we have for the periodic system. And just let me show this. We have done this for several years. I'm just going to show this one. This is the periodic system by 1869 using data, using the chemical space between 1800 and 1869. Then what we have here is the size of the nodes, is the percentage, what I want to say here is that if hydrogen is high, it's very big, it's because a lot of substances in the chemical space by 1869 included hydrogen. The same with carbon, oxygen, and then here you see that most of the substances by that time were kind of organic substances. The arrows indicate whether one substance is similar to the other. For example, by 1869, according to our data, hydrogen was very similar to potassium. Oxygen was very similar to sulfur, and sulfur was very similar to oxygen. And yeah, that's more or less the idea. And the results we have, but I don't want to show that here. The result is that every year we know the shape of the periodic system, and then is something like connecting the evolution of a concept, which is the periodic system, with the evolution of chemical knowledge, with the evolution of the chemical space. Yeah, and with that, I would like to say that in order to explore in this way the chemical knowledge, we need mathematicians. Oh, sorry. Okay, yeah, we need mathematicians, computer sciences, historians. We need chemists, of course. We need interdisciplinary work here. Yeah, with that, I would like to thank Andrés Bernal, Jürgen Jost, Wilmer Leal. For example, Wilmer Leal and Eugenio Llanos, they did a lot of work processing the data. Duke Lu worked heavily on the time series analysis. Peter Stadler, Jürgen Jost worked also on the discussion of the results and in the setting of the experiments. And Andrés Bernal was behind the discussion on the periodic system and the evolution of that. Thank you to all those agencies giving us money to play with this. And with that, muchas gracias.
Thank you. We have 5 more minutes left for Q&A. And there was a question by Farzad.
Hi, Guillermo. Thank you for the great talk. As usual, very exciting. One question, you mentioned that by understanding large-scale patterns that are extrapolatable into the future, we could kind of not just see where it's been, but where it's going. And I just wanted to ask you if you could imagine an example that you could give us. And I guess thinking about the wars as a horrible stimulus, but also a slowdown of innovation. There are both, good, like green chemistry things, and also evil ways of, social systems driving these things. But with all that in mind, do you have an example that you could share about the large-scale patterns kind of indicating a future for chemical discovery?
Yeah. I think one large-scale pattern is, for example, the periodic system. I don't want to do here something like or to be like a spoiler here. But I could just mention that it seems, according to our data, that the patterns, for example, of similarity in the periodic system, they are kind of converging. Then the chemical space is expanding, and it seems, according to our results, there are some similarities that year after year they are reinforcing and reinforcing and reinforcing. That means that the periodic system is something like converging, even if we are doing very weird chemistry. Even if we are now making helium with some other elements, even if we are doing high pressure chemistry at very extreme pressure, even with that, we have that there are some regularities in that. Another example is, for instance, the drug industry, the pharmaceutical companies, they are interested in populating that subspace of, for example, oral drug-like substances. That's the so-called Lipinski space. Then we have seen that there are some regularities in the way chemists have populated that space. Then we could say, for instance, that in the future, they are going to be more or less with 1 bar error, this number of substances belonging to that important space for chemistry. And yeah, there are several others. Your mic is open.
Thank you. A quick follow-up on that. It seems to be then you're with the convergence and noting these regularities, which is of course a great way to do science. There seems to be, though, a sort of a continuity, looking for content or finding continuity. I guess I'm concerned about the spaces that are not explored because of things like the Lipinski space. I mean, that kind of drives everything already in one direction, or the tendency to use just certain solvents that you pointed out. Are we just are you just predicting a future based on these very limited sets of things we're doing now?
Yeah, that's totally right. What you are saying is totally right. And because of that, we need to consider not only the material system, we need to see in which context those developments have taken place. Then we need to consider the social system and also the semiotic system. The problem is that we have a fantastic database of the material system, but historians of chemistry are not that good in collecting all the sources of information they have in one single database. That's something to do in history of chemistry, to create a database for history of chemistry, of social factors, for instance, and also on the semiotic side, there is nothing. There is nothing collecting all the semiotic ways of communicating results in chemistry. We need to create those databases to try to do what we are doing with the material system, but we need to consider that, yeah.
Thank you.
So I'm afraid our time's up, but there are 2 more questions from Michelle and Olympia.
Only one by Michelle. I can ask him later, but there is one from Michelle before.
Okay, it's just very quick. It's very impressive that the number of chemicals and have doubled every 16 years, but that can't go on continuously. So at some point the curve is going to flatten out, right? So do you have any ideas when that will happen?
Yeah, very good question. In the 60s, Solar Price was the first one in starting to use the methods of mathematics and physics to understand the growth of science. And he said in the 60s that that plateau, that saturation point was kind of, we were in the 60s reaching that plateau, but he was wrong. Yeah, as we say here, he was wrong. We haven't seen but that's true. There are some, and the point is to try to see when that's going to happen, knowing what is happening socially and semiotically. If we know that, then we can try to see when that is going to be flat.
And with technological innovations, because with new instruments and possibilities, it suddenly upscales again really fast.
Yeah.
So,
true. But
we can't have an infinite number of laboratories on Earth, right? So know, at some
But no, but yeah, that's one point. Yeah, and we need also to consider the growth of the scientific community. That's also very important, and that has to do, for example, with how popular it is to study chemistry. Then you need to and that goes back again to study the social system. Yeah, but yeah, that plateau could be reached hopefully very far in the future.
Okay, well, let's thank Guillermo once more for a very nice talk.
Thank you.